Okay, I guess that was the message that we can start. It's about 9:10, perfectly on our delayed starting time. Okay, good morning, everybody. I hope everybody is doing well and ready for another full day of lectures. I was tasked, or actually, I volunteered to give an overview of modern theories of monsoons, ITCZ, and I'll tell you a little bit how I decided to structure this lecture, but I really wanted to connect to some of the things that were already discussed yesterday. So I will start with a very brief overview of monsoon systems with a little bit of an emphasis on the larger scale monsoons in the Northern Hemisphere. Then I'll touch upon, again, how we have recently been thinking about them as we will see cross-equatorial Hadley circulations. This will connect to some of the things that Spencer was discussing yesterday during the very last lecture. And then we'll get a little bit more into, again, what we have learned about monsoons with three idealized numerical experiments and questions that remain open. Of course, as always, this is a personal view of monsoon theories because this is really a topic I spent quite a lot of time thinking about throughout my career. Okay, so let's start with really the traditional definition of monsoons. As probably you all know, the word monsoon comes from the Arabic word mausim, for seasons. And that is because for the sailors in the past that used shipping routes over the Indian Ocean, really the most defining aspects of the passing of the season was the seasonal reversal in the lower level winds that blow from the northeast to the southwest during the winter months. Of course, here we're focusing on the northern hemisphere, and reverse completely during the summer months. And clearly you see, and we'll spend a little bit more time seeing how this establishes itself. We see the development of this strong cross-equatorial southwesterly flow over, again, the Indian region. The first account of world monsoons dates back to Ramage, 1971, where several criteria were introduced to really define a monsoon system. And these criteria were that prevailing winds needed to shift at least 120 degrees between winter and summer. The average frequency of prevailing winds needed to be larger than 40%, so not just and a speed of the mean winds exceeds 3 meters per second. So again, this criteria really emphasize reversal of the winds, but also steadiness of the winds, and pressure patterns satisfy a certain steadiness criterion. And so this is the classic monsoon region identified through this monsoon definitions. And so notice how there is no monsoon identified over the Americas. Also over South Africa, notice how through this definition, we have really a monsoon that basically extends over East Asia almost all the way to 60 degrees. And so the Asian monsoon, of course, we all know is the largest monsoon system, and it's divided in several subsystems. I won't go through them all, but let's just say that this is the Indian South Asian monsoon. This is the traditional East Asian monsoon, which, as you can see, is the one that tends to extend further poleward, that in fact is a mixed system, is a system that has tropical characteristics, but also strongly influenced by what happens in the extratropics. And then we have the Western Pacific monsoon. Again, I want to show you some observed features of the South Asian monsoon, because this will provide some inspiration for some of the more traditional definitions of monsoons and some of the things that we want to capture, for instance, when we model monsoons in idealized settings. So I'm going to show you, and in fact, I'm going to start it because this will repeat. In animation, this is based on GPCP, precipitation and MERA2 near surface winds. We started on January 1st, and here, again, we're seeing the evolution of the long-term daily averages of winds and precipitation. And I really like this animation because it really clearly shows the large changes that precipitation and winds undergo in this through the annual cycle in this region. Again, I'll let it loop through again. Again, now we're going towards the winter. In the winter, we clearly see northeasterly flow through the region. Rain is primarily located south of the equator. And notice how now in May, things happen quite rapidly. The southwesterly, cross-equatorial southwesterly flow gets established really quickly. And you see that basically the development of precipitation north of the equator and the establishment of rains over the Indian subcontinent follow, again, quite rapidly. Again, let's look at this again. And then we see that later in the at the end of the summer and in the fall, we see a similar retreat, although it happens a little bit more slowly. So clearly we see that these changes, as I mentioned, occur somewhat rapidly. And let me try to characterize the rapidity of monsoon onset a little bit more clearly by showing you in a Hofmöller diagram, latitude versus time in Julian day, of the precipitation averaged in longitude between 60 and 100 degrees east. So really are looking at the core of the Indian monsoon where the Indian peninsula is located. And so you clearly see that during the winter months, the season that is dry over the Indian subcontinent, rains are primarily organized along a convergence zone that is sitting south of the equator, close but south of the equator. And then you see that at the beginning of the warm season, again, this the onset of the monsoon really appears as a rapid rearrangement of this precipitation patterns, with now the major convergence zone shifting rapidly into the northern hemisphere subtropics, again, where the continent is located. And you clearly see that this is a rapid onset, the time scale associated with this rearrangement of the precipitation patterns that we know are also accompanied by changes in the circulation patterns occur on a time scale of about 2 weeks. This is faster than what can just be interpreted as a linear response to the smoothly varying insolation. So clearly, there is a rapid onset. Even if we believe that, of course, monsoons are a response to the insolation forcing, there must be some nonlinearities that are implicated in this rapid response or most smoothly varying insolation forcing. Let me show you what the upper level flow looks like. These are streamlines of the 200 hectopascal flow, and the shading represent the absolute vorticity. And again, notice how in July, when the monsoon has reached maturity, we see the establishment of this very broad monsoon anticyclone. This is not unlike what we see in the North American monsoon, how we clearly saw yesterday. Here we don't see the animation, we just see the establishment of these patterns in July. Because I will try to convince you that now we really think about monsoons as, or at least large-scale monsoons, as cross-equatorial Hadley circulations, let me try to set a little bit the observational stage for that interpretation. So this is the distribution in the meridional plane, again, pressure or height versus latitude of the zonal winds in the line contours, with easterly where you see the dashed line, westerly when you see the solid line, the zero line is thickened, and shading represents the meridional winds, again, averaged over the sector of the Indian monsoon between 60 and 100 degrees east. And here the things that I want to highlight is the fact that again, we'll return to what it really means to have a structure, to see in a returning circulation that has a structure of a cross-equatorial Hadley cell, but I hope that everybody can see that in this region at low levels, we see positive meridional flow. This is northward flow that crosses the equator. And in upper levels, we see an oppositely signed flow still crossing the equator from the northern to the southern hemisphere. And of course, one could imagine that to close the circulation, you would get vertical upward motion in this region, downward motion in this region. In terms of the zonal winds, I want to emphasize how near the surface, and in fact, almost extending to the mid-troposphere, you see the establishment of this westerly flow. This is the component, the westerly component of the near surface flow that we saw in the animation. We see broad upper level easterlies that really span from basically 30 degrees north to about 10 degrees south, flanked by westerly jets, one in the subtropics of the southern hemisphere, which is the winter hemisphere, very strong, one weaker further poleward in the summer hemisphere. And this reminds some patterns that Spencer described through more analytical models. You're right, but we'll get back to this later on. Just a few words about the Western African monsoon, which is another large-scale monsoon in the northern hemisphere. Again, as before, here we see the precipitation and near-surface winds patterns for, sorry, here I forgot to mention DJF, and this one is JJA. And we clearly see that, as in the case of the South Asian monsoon, we clearly see a rapid shift. Well, we don't see the rapidity here, but we see that during the summer, the rainfall bands moves into the sub-Saharan African region. And this is also, there's a shift of the ITCC in the subtropical summertime African continent is accompanied by a reversal of the winds similar to what we saw in the monsoon region. If we focus especially in the region where we see summer rains, we see that this warm, dry Harmattan winds are being replaced by the moister southwesterly flow. One interesting feature of the wind distribution and the precipitation patterns in the Western African monsoon is that you find that the intertropical discontinuity, as this line is called, these are just drew a straight line to make things simple, but this is basically where the maximum low-level convergence is occurring. Notice how, again, this is where the boundary between the moist southwesterly flow and the dry Harmattan winds, this is located poleward of the maximum rainfall. And this is an interesting feature of the Western African monsoon. And this is the Hofmöller diagram, again, focusing on the core of the basically Sahel region, just to show that we do see rapid transitions in the establishment of the African monsoon. In reality, we see maybe two different transitions. One in around May, where again the core of the precipitation shifts from the near equatorial region into the basically the coastal region, and then later on you see another jump in July where precipitation further inland. So we still see rapid transitions, although the seasonality is a little bit more complex than one we see over the South Asian monsoon. As before, let's look at the distribution of the zonal and meridional winds in the meridional plain, again, averaged over the core of the Western African monsoon. Again, notice how, again, as before, shading meridional wind line contours zonal winds. As before, notice how we see this deep, strong poleward, I should say northward flow from the southern to the northern hemisphere crossing the equator. And we see the existence of a reversed flow that goes from the north to the south, also across the equator. But notice how the near surface northward flow extends further poleward than where we see the beginning of the oppositely signed flow in the upper troposphere. And in fact, we will see that for the Western African monsoon, the circulation structure is a bit more complex. We have a deep overturning circulation whose ascending branch is located at about 10 degrees north, and this is really what is associated with the deep monsoonal circulation. But we have a shallow overturning that is found northward of this. Again, this is basically the near level flow, and this is the return flow that is happening at lower to mid levels, and this is the shallow circulation that develops over the Sahara that in fact is importing drier air into the deep monsoonal circulation, and whose interaction with the monsoonal circulation is yet not completely understood. And then again, notice how in terms of the zonal winds, the patterns look very similar, at least in terms of the presence of a westerly flow close to the surface, upper level easterlies flanked by westerly jets, both to the south and the north. Again, let me also emphasize in terms of the distribution of the zonal winds, how there is the existence of this African easterly jet, this one here, that is really one of the hallmark of the development, of the circulation over Africa during the summer. It has a lot of implications also downstream because eddies that form through instabilities of the African easterly jet are seeds for the development of tropical storms over the Atlantic. And this African easterly jet really develops because over Africa you have this reverse meridional temperature gradient. And so going back to thermal wind that Spencer introduced yesterday, usually we have a gradient in which temperatures are higher close to the equator, and then they decrease as we move forward, and this implies a westerly shear. So wind that becomes increasingly westerly with height, here in the presence of a reverse meridional temperature gradient, we develop an easterly jet. And let me emphasize how we clearly see, even in this meridional plane through the distribution of both the zonal and the meridional winds, that the intertropical discontinuity really represents the latitude at around this latitude band around 20 degrees, with both the zonal and the meridional wind change sign at lower levels. And again, this is just a schematic of some of the things that I've discussed. I don't want to go too much into details here. I'm happy to go back to this if there's questions. We have a lot to cover. So I just wanted to use this as really a motivation to think a little bit more deeply as to what might be driving mechanisms for monsoonal circulations. And this is a schematic that I borrowed from Rudiman, 2007. This is a textbook that is used extensively in the US and I think elsewhere as well, as an introduction to the basics of basically climate. And in this textbook, the depiction of monsoons as continental scale sea breeze circulations, as you still reproduce, this is something, I think this is how we all learn about monsoons in grade schools. This is for sure how my kids to these days have learned about monsoons in grade school. And so basically this traditional definition interprets these circulations as large-scale sea breezes that are driven by the contrast in thermal properties between, let's say, subtropical continent and a nearby, more equatorial ocean, in which, thanks to its much smaller heat capacity, the continent can heat up faster during the summer, cool off faster during the winter, and this drives circulations that reverse direction with associated precipitation patterns in the seasons. But let me here emphasize how recent definitions have shifted this interpretation to of monsoons to view them as really a vital part of the tropical atmospheric overturning. And so let me here try to really tell you a little bit more what is the evidence that has really that has driven this shift on how we view monsoons. And let me start by showing you large-scale precipitation patterns. This is just for the annual mean. Again, there's a couple of things that I want to say about the distribution of the annual mean precipitation. Again, this is from GPCP. Again, I'm sure that you all know this distribution really well. I really just here want to emphasize that we clearly see that, of course, it rains a lot in the tropics, and this rain is primarily concentrated over the ocean in bands that are narrow in latitude, extended in longitude. We see this almost over all tropical ocean basins. We clearly see broader convergence zones over the oceans, and we'll see, over the continents, and we'll see that this is really the imprint on the annual mean of a strong annual cycle of precipitation there. So if we now take a zonal average for each longitude, this is what we obtain. This is the distribution as a function of latitude of the zonally averaged precipitation. And we clearly retrieve the very familiar pattern of wetter and drier zones with the wettest band located close to the equator, the dry regions in the subtropics, and two broad wetter regions in the mid-latitudes of both hemispheres. But one thing that I want to point your attention to is the fact that in this distribution of the zonally average precipitation, we clearly see that the maximum precipitation is not located at the equator, but is located north of the equator. Well, one might think, well, why should precipitation maximize at the equator? One could imagine maybe a double lattice structure. But of course, the other interesting thing here is that we do not see a structure that is symmetric about the equator. So on average, we clearly see that precipitation prefers the northern hemisphere. And why is that the case? This is a question that has been addressed extensively in the literature. Of course, this implies the existence of a hemispheric asymmetry that makes the northern hemisphere more favorable for precipitation. And let me just say that many different hypotheses have been put forward, and consensus has emerged only in the past, I would say, 10 years or so. And I'm happy to return to this in more details if there is interest. But let me just say that if you're thinking that the fact that the ITCZ is shifted north of the equator might be due to the fact that there is more continents in the northern hemisphere, and therefore that hemisphere is warmer, you actually are wrong. It turns out that we now think that really what is making the northern hemisphere warmer is the fact that in the Atlantic, the meridional oceanic overturning circulation is transporting energy from the southern to the northern hemisphere. And for reasons that hopefully will become clear as part of this talk, it's the atmospheric circulation that needs to transport energy back from the northern to the southern hemisphere, even in the annual mean. And it does so by shifting the ascending branch of the southern Hadley cell north of the equator. But again, if this didn't make too much sense, I hope that towards the end of this talk, maybe things will start coming together a bit more easily. Again, because I really want to emphasize the link between the zonally average precipitation and the overturning circulation, let me show you here the observed patterns of the Hadley cell in the meridional pressure versus latitude plane for the annual average. As we all know, probably, the Hadley cells in the annual mean are characterized by two, the Hadley cell pattern in the annual or in the equinox means is characterized by two cells, the southern and the northern cell, that are almost but not completely symmetric about the equator. Notice how the southern cell is slightly broader and stronger than the northern cell. We clearly see the dividing boundary between the southern and the northern cell, while coincides with this peak in precipitation north of the equator. And it's clear that, again, this peak in precipitation really is associated with the ascending motion within the ascending branch of the Hadley cell, whereas the dry regions are located under the influence of the descending branches. I didn't put this back up in my presentation, but if you go back to my lecture yesterday, I showed you patterns of the observed relative humidity in the meridional plane, and I hinted to the fact that in the ascending branch of the Hadley cell, we saw somewhat more homogeneous and higher relative humidity patterns, and I pointed to the existence of this very dry pockets of very dry air in the mid-troposphere in the subtropics. And again, this is primarily arising from the descending branches of the Hadley cell. Not completely, but primarily arising from the descending branches of the Hadley cell. But now, of course, because we are interested in monsoons, I want to show you the corresponding precipitation patterns average for the month of July, Northern Hemisphere summer, and for the month of January, Southern Hemisphere summer. And I'm going to be toggling between the two. And first of all, I want you to focus your attention on the oceans. So pick your ocean basins you like the most, but one obvious one is the Pacific Ocean. And notice there how we clearly see a seasonality. On average, we do tend to see that precipitation tends to move towards the summer hemisphere. But notice how, again, the seasonality over the oceans tend to be a bit more muted. Notice, for instance, how for large stretches of the central and eastern Pacific Ocean, the precipitation maximum remains north of the equator, even if insolation is maximizing south of the equator. And so precipitation maxima do not always follow the insolation maximum. Now, instead, focus your attention on a tropical, subtropical continent that you like. It could be northern or southern hemisphere. Of course, here an obvious choice is the Southeast Asian monsoon region. And there we clearly see that precipitation has a much larger seasonality. characterized by very dry winters followed by very wet summers. And I hope that everybody can see how, in reality, the rainfall bands that move into all subtropical continents really appear as an extension of the oceanic ITCZs. And so it's really this, and again, let me emphasize how we see this shift of rainfall bands into subtropical continents on all continents, both in the northern and the southern hemisphere. And so this recognition has really led to a shift towards more precipitation-centric definitions of monsoons that clearly emphasize monsoons as well-defined summertime precipitation maxima, and linking much more clearly the development of these systems to the seasonal evolution of the tropical overturning and the associated ascending regions where we have a convergence and development of precipitation. And I want to really maybe characterize, I already showed you how over both the Indian and the African monsoon sector, we clearly see the development of meridional wind patterns that resemble the development of a cross-equatorial overturning circulation. But let me try to make this link a little bit more clear. So now here I'm showing the pattern of the global Hadley cell. So we're still averaging over the 360 degrees for the month of July. And let me compare this to the pattern that I showed you here. So this is the annual average, again, characterized by this equinoctial pattern with two cells that are almost, not completely, but almost symmetric about the equator. And this is the solstitial pattern. This is what we see in July, where you clearly see that the overturning circulation is dominated by just one single cell. This is the winter cell because it's the southern cell. The southern hemisphere is it's the winter hemisphere. This is the winter cell that has strengthened and has broadened so much that the northern cell, you don't even see here, is very, very narrow, very, very weak. And this cross-equatorial Hadley cell has shifted its ascending branch into the summer hemisphere, further poleward than we see in the annual mean, with cross-equatorial, well-defined cross-equatorial flow, both at low and upper levels. If now, instead of taking a complete zonal mean, we average, again, over the Indian monsoon sector that we already spent quite some time thinking about, this is the overturning circulation that is established in July. That is to say that the onset of monsoon rains is really associated with the development of a monsoonal overturning cell that looks very much like a cross-equatorial Hadley circulation. It's even broader than what we see in the zonal mean, because of course, when you take the zonal mean, you also have the contribution for the oceanic sectors where things remain more confined towards the equator. And so here I'm really just summarizing with just one statement work that has been done in the past 15 to 20 years. Here I'm pointing to some of the work that we have done in my group, but of course, it's not, this shift is not just based on work from my group, and outside more papers later on. And really now we really think about at least large-scale monsoonal circulations as cross-equatorial Hadley cells that project strongly on the solstice zonal mean. We will see that the North American monsoon, as maybe is already clear to many of you, probably is the one monsoon that shows significant deviations from this emerging view of larger scale monsoon systems. And it was already pointed out yesterday how, in fact, the kind of this poleward extension of the monsoon rains, what we really identify as a North American monsoon, probably cannot be interpreted as an extension of the oceanic ITCZ from the Eastern Pacific. So in maybe parallel to this development from this theoretical development of monsoons as cross-equatorial overturning circulation, a complementary view has emerged that has led to the introduction of this term, the global monsoon. These views are very complementary. And so let me try to emphasize what the global monsoon, what we mean by the global monsoon. So this is a similar plot to the one that was shown yesterday. This the shading shows the difference between the precipitation average during the northern hemisphere and minus the difference between the northern hemisphere and southern hemisphere summer. And the vectors show the same, but for the lower level winds. And it is clear here we see all of the different monsoon systems really emerging as well-defined summertime precipitation maxima, accompanied by changes, reversals in the low-level circulation. If now we do an EOF analysis of the annual cycle of combined precipitation and low-level winds, what emerges as a dominant mode is a first EOF that explains 71% of that variability and whose pattern, which is shown here, shadings, precipitation, vectors, low-level circulation, very much look like this. And so really we see that basically there emerges this dominant mode in the annual cycle of precipitation and circulation that really represents, again, this global response with regional manifestations in the different monsoon regions. It's really the dominant response of the overall precipitation and circulation patterns in the tropic to the annual cycle of insolation. And this is really this basically coherent response of the precipitation and circulation patterns in the tropics has been dubbed as the global monsoon. That is, of course, not to say that the different monsoon systems do not respond differently to forcings that act on different time scales, but at least in terms of the annual cycle, you really see this coherent behavior. And so let me here emphasize how I think that now there is a quite strong agreement in the community that monsoons, at least the large-scale monsoons, should really not be thought as land sea breeze circulations that are driven by the near-surface meridional temperature gradients. And in fact, we should think of monsoons as cross-equatorial Hadley circulations. And as Spencer yesterday emphasized so much, it's important to really think about these circulations, even regional manifestations in monsoon regions, as part of this, again,